Okay, before we begin, can I please get confirmation that you guys can hear me and see my screen and everything is cool? Perfect. So let's begin. Okay, so today we're going to be Assalamu alaikum and good morning, guys. Welcome back to Physics Grade 12 by Inspired Teens. In today's lesson, we're going to be starting with organic chemistry. Okay, so obviously we're not going to be able to get all the way to the end. Organic chemistry is a big topic, but we're going to be covering it completely, entirely over the next few weeks. Okay, so let us get started. Okay, so the first thing to talk about in organic chemistry, okay, so organic chemistry, maybe it's a bit challenging now, maybe you find that it's a lot, okay, but, okay, organic chemistry, towards the end, you'll see, you'll regard as one of your easiest topics, okay, because once you get a good understanding for it, okay, you'll see that the questions cannot be different, okay, once you understand all your theory, it's a lot, right? It's the biggest section in your test, I believe. So it's actually a good section to score marks in. Okay, I would say all, like even the reactions, right? Once you know it, it can be easy. It's just a lot to study. Okay, once you know your rules properly, it's again one of the easiest sections, if not the easiest section, or you can score a lot of marks in. Okay, so if I was you, I'd push in the section to understand it completely, and I think it's worth like what, like 47 marks or 30 something marks to try and get close to full marks for this section. So the first thing we need to know, okay, in organic chemistry is about our homologous series. Okay, in organic chemistry, okay, we'll be dealing a lot with carbon. Okay, and we need to note, what's a nice color? Black. We need to note, okay, that carbon can create 4 bonds. Okay, so carbon can create 4 bonds. Okay, 75 marks in my paper this term. Yeah, okay, that makes sense, right? This term, obviously, it's going to be a majority of your marks because you've only done very little topics. Okay, but I'm saying like in the final exam. Okay, then we move on to discuss our different homologous series. So we have 5, 6, 7, 8, 9. We have 9 homologous series in total. The first 3 are known as hydrocarbons. So why are they known as hydrocarbons? Simply because they only contain hydrogen and they only contain carbon. Okay, so that's why they're known as hydrocarbons. They are the alkane, the alkene, and the alkyne. Okay, so don't worry about that ein, ein, ein thing. That's the suffix which we'll talk about when we start naming organic compounds. Okay, so all of our homologous series, okay, we have their general formulas, which are highlighted in green. Okay, so this is what's known as the general formula. And on the right, okay, we have the functional group. Okay, so the general formula describes to us mathematically how many carbons we have and how many hydrogens we have. Okay, so it's basically telling you for a specific amount of carbons, how many hydrogen you're going to have. Okay, so if I want an alkane, so if my general formula of my alkane is CnH2n plus 2. So if I have 5 carbons, I can then calculate how many hydrogens am I going to have? 2 times 5, okay, plus 2. So when I have 5 carbons, okay, I have 10 plus 2, I have 12 hydrogens. Okay, so that's basically what the general formula is telling us about. Then we have alkene. Okay, so our alkene is CnH2n, so it has double the amount of hydrogens compared to carbon. Then we have alkyne, which is times 2 minus 2. Okay, then we have the functional group. So what is a functional group? Okay, a functional group actually is the specific part of an organic compound that makes it belong to the homologous series. Okay, so each homologous series, we can write that under here. Each homologous series has their own functional group. Okay, so it's a defining structure of an organic compound. A functional group, it's the defining structure of an organic compound. Okay, so here we can see that an alkane is actually defined by a single bond. As it can be seen there. An alkene is defined by a double bond. Okay, and the structure of an alkyne is a triple bond. Okay, so that's what would indicate and distinguish an alkane from the rest of the compounds, and an alkene from the rest of the compounds, and an alkyne for the rest of the from the rest of the compounds. Okay, let's move on. Okay, to haloalkanes. Okay, so it's an alkane. It's a type of an alkane. Okay, so it's going to have hydrogen and carbon. However, the halo part comes from the fact that haloalkanes have halogens or halogens or whatever you want to say. You want to call it a halogen, potato. Okay. Okay, so they have halogens. Now, what are our halogens? Our halogens are our group 17, I believe, group 17 gases. It's the second last group, group. I think it's a group. Vertical columns in the periodic table, I think they call groups. It's the second last group in the periodic table. Okay, it consists of Cl, Br. Jeez, it's been a while since I looked at the periodic table. Give me all the halogens, someone please. Bromine, iodine, chlorine, bromine, iodine. Fluorine, that's the one I'm missing, thanks. Okay, so those are the halogens, like the main ones you work with from the second last group in the periodic table. Okay, so as you can see, the defining structure of a haloalkane or a haloalkane, okay, is the fact that it has a halogen. So it's an alkane, meaning it has a single bond, not a kene. Okay, so it doesn't have a double bond. Okay, so it has a single bond, but it also has a halogen attached to it. And like I said, that is the defining structure to tell us, okay, this is a haloalkane. Okay, then we move on. We have an alcohol. Okay, the defining structure of an alcohol is that it has an OH attached to it, a hydrogen and an oxygen attached to it. Okay, so these are what we call, again, the functional groups. Okay, so we'll do an example, okay, when we do naming, but even before we get there, let's just add a page and we'll do an example. So this is an alcohol, okay? The general formula is as follows. So CnH2n plus 1, and then an extra OH at the end. Okay, it makes sense. Alternatively, you could take this H and add it into that calculation. So it becomes plus 2 and just O. Okay, so we have an alcohol in this case. And again, like I said, the functional group or the defining structure of the alcohol is actually the OH. So what does that mean? It basically means that I can create alcohols, right? So in organic chemistry, remember I said we work with C, carbon. Now carbon can create 4 bonds. Okay, 4 bonds. And the more carbons we have different names for it. Okay, so I can create an alcohol with 2 carbons. I can create an alcohol with 4 carbons. Okay, but the thing that makes it an alcohol is the fact that it has OH. So I can start off with an OH. okay, bond it to a carbon, and here I have an alcohol. Okay, this is an alcohol with one carbon. Okay, I can create an alcohol, OH, as long as I'm drawing its functional group, and I can bond it to 3 carbons. Okay, just keep in mind, see, I am keeping 4 bonds per carbon. Okay, that's really important. So I have my alcohol, and then the rest of the carbons are bonded to hydrogens. So this is an alcohol. How do I know it's an alcohol? Just simply due to the fact that I can see the structure. Okay, it has the functional group of an alcohol, meaning it has OH. This tells us, okay, this is an alcohol. Okay, and this is an alcohol with 3 carbons. Okay, so yes, the same could be said for an alkane. You could have an alkane with 3 carbons, 4 carbons, 5 carbons, we learn up to 8 carbons. An alkene with that amount of carbons, an alkyne with that amount of carbons, a haloalkane with that amount of carbons, an alcohol. Okay, then we have something called a carboxylic acid. Okay, before we move on, these are some of the functional groups have names, and we have to know them. So these are the names of the functional groups. Okay, remember, what did we say was a functional group? Functional group is basically, if you just had to have an understanding definition, a functional group, right, is the defining structure of a homologous series. So the homologous series, right, sounds like a fancy name, but it's basically just each of these are their own homologous series, right? They belong to their own homologous series. Okay, so it's the different types of chemical, it's the different types of organic compounds that we're learning about. Okay, this is organic chemistry, all right? And the functional group, each homologous series, what makes each homologous series different is the functional group. Okay, and yes, it's the defining structure of each organic compound. So for example, an alkane. What is the functional group of an alkane? It just shows us a single bond. That means, okay, if we only have hydrogens and carbons and single bonds only, that would be referred to as an alkane. But the second we add a double bond to that hydrocarbon or to that organic compound, we create an alkene. The second we add a triple bond, we create an alkyne. Okay. Similarly, if we have a halogen in our organic compound, that would mean, okay, this is a haloalkane. Then if we have OH, okay, in just like OH, right, then we say, okay, this is an alcohol. So that's how you define your different organic compounds, just by the presence of their functional group. Yes, and all the functional groups are drawn. And again, some of these functional groups have names and we need to know their names. So for example, the functional group of an alcohol is known as a hydroxyl. So this compound here is known as a hydroxyl. Okay, then we move on to carboxylic acid. Now, carboxylic acid has the following general formula. So you need to know your general formulas as well. You'll see why when we eventually do questions, right? They incorporate it in the questions and they expect you to know a compound, be able to distinguish a compound just from knowing its general formula, knowing how many carbons it's supposed to have, knowing how many hydrogens it's supposed to have, and for some compounds, knowing how many oxygens it's supposed to have, right? So as you can see here, this is the functional group of a carboxylic acid. It's slightly more complex, right? Whereas it has a OH, okay, it's not an alcohol, okay? It has an OH and it has a double bonded O. That is it. The defining structure of a carboxylic acid is this compound here. We have a carbon. So basically, I'm telling you that every single carboxylic acid will have this, okay? Where we have a carbon, double bonded to an oxygen on top, bottom, wherever, it doesn't really matter. And that same carbon is bonded on another side to an oxygen, and then that oxygen is bonded to a hydrogen. Okay, we can call this a hydroxyl. So it has a hydroxyl and it has a double bonded O. And you'll see that this carbon, why do I not have another hydrogen sticking out here? Because remember we said that carbon can only form 4 bonds and it's used up its 4 bonds already. 1, 2, 3, 4. So just keep that in mind. It needs to form 4 bonds. So this one here, this lead at the end here, this is going to attach to more carbons if it needs to, right? So that's how we create different carboxylic acids with a different amount of carbons. Okay, and just this is, we'll learn the different structures in a bit. This is actually called the semi-condensed. I'll write it now, I guess. Semi-condensed structural formula. Okay. I should have written it in blue, but it's fine. This is the semi-condensed structural formula. We'll learn it in a bit, and it's just it makes more sense sometimes. And it just I put it here because it's easier to just remember it as that. So we remember the carboxylic acids functional group as Cu. Okay, that's Cu, meaning remember, oh, okay, it has the C double bonded to the O and then the OH minus. Cu. Okay, then this functional group also has a name. It's known as the carboxyl. Okay, so carboxylic acid, carboxyl makes sense. Then we have something called the ester, and there's a reason that the carboxylic acids are like sort of kept together. Sorry, carboxylic acid and esters are sort of grouped together, and aldehydes and ketones are sort of grouped together. We'll learn that reason a bit later. Okay, so let's talk about it, right? So let's look at an ester. The general formula, the general equation is CnH2NO2, perfectly fine. And then we can have a look at its, so you have to know properly the functional groups. You have to know how to draw the functional groups. These are actually what we refer to as the structural. Okay, I'm not going to get into that because we're going to do the different formulas next, right? Then you can understand. But basically, yes, you have to know the functional group. Every time you need to draw up a organic compound, you start off with its functional group and you take it from there. Okay, so in this case, for every single ester that you draw, you're going to start drawing with this base. This is going to be your base, your functional group. Okay, so in this case, you can see a C double bonded to an O, and then that C is bonded to another O and then bonded to another C. So you can actually extend C's on either side of this ester. Okay, and this one, semi-condensed, Cook. Okay, just to remember it purposes. And also, you'll see when you are given semi-condensed, you will see this in the semi-condensed, and that's how you will know what type of homologous series that compound belongs to. Yes, this functional group has a name. It is known as the carbonyl. Then we have an aldehyde. So an aldehyde, its general formula is CnH2nO. As you can see, the functional group is given. Okay, it is a C double bonded to an O, and then it ends with a H. Okay, because remember, H's can only form one bond. That's also important to note. Hydrogens can only form a single bond. Right, 2 electrons. So, which we can see, C double bonded to an O, bonded to an H. We abbreviate this as CHO, okay? And this functional group is known as a 4-mile. Okay, cool. Then its partner, let's just say, ketones, CnH2nO. And we can see that, okay, the functional group of a ketone is that it has that double bonded O, okay, a C double bonded to an O, and C's on either end. A C on either end of that main C. Now, a ketone has to have a minimum of 3 carbons. The reason for that is because if I have to draw a ketone with 2 carbons, so just say I don't want more carbons. This is it. I just want this amount of carbons, right? I'd have to end here in an H. Then we'll notice that, hey, this is actually CHO. This is CHO. Okay. This is our CHO. And then therefore, this is not a ketone anymore. It's an aldehyde. Okay. So minimum amount of 3 carbons for our ketones because of that specific reason, that our functional group is a C double bonded to an O, which needs to have C's on either end. Okay. I'm not saying that, but it's a semi-condensed COC, and it's also called a carbonyl. Okay, C double bonded to an O, basically. Okay, I hope that makes sense so far. All right, so the basics, again, it's just theory type thing. There's nothing that we've put into practice yet, but it makes sense so far, right? So these are our different types of homologous series. their functional groups, their general formulas, the names of their functional groups, and the semi-condensed structural formulas of the functional groups as well. Okay, so let's move on. We're going to talk about what? We're going to talk about the different types of formulas that we get. Okay, the first of which is known as the general formula, which we learned about. The second of which we're going to learn about is the molecular formula. The third of which is known as the semi-condensed structural formula. And finally, we're going to learn about the structural formula. Okay, so the general formula are the general formulas on the first page that we need to know. So for example, for an alkane, it's CnH2n plus 2. Okay, so it's basically saying for every N I have 2 times that amount plus 2. So then we're going to move on to structural formula. So structural formula is basically the drawing of the compound. So let's just say I'm dealing with the alkene. Sorry, let's write it down here. C5. I want 5 carbons, so I'm going to have CnH2 times 5 plus 2. So C5, H2 times 5 is 10, H12, basically. So if I want to know what is the structural formula is actually the structure, the drawing. So I will draw 5 carbons. 1, 2, 3, 4, 5. What is the functional group of an alkane? Because this is what I'm drawing, an alkane. It is basically a single bond. So that's it, all single bonds, right? And then I can finish it off. So each carbon, like the edge carbons, for example, they can take 3 hydrogens because they need to fill up and have 4. But however, the middle ones can only take 2 more because one is bonded with the C on the left, one is bonded with the C on the right. Okay, so that's the structural formula coming from the general formula. Molecular formula is simple. Okay, it is basically the general formula, but filled in with the actual amounts of carbon and hydrogen. So you're not having it in terms of the formula, you're writing it with the actual amounts of carbon and hydrogen in the question. So for example, in our specific thing, we said C5H12. That was our alkane that we drew. So you're filling in the numbers of carbons and numbers of hydrogens. Okay, so general formula, structural formula, molecular formula. Then we talk about the semi-condensed structural formula. Now, the semi-condensed structural formula is basically like the molecular formula, but we do it with each individual C. Okay, so if we start off with our first C, attached to our first C is an H, not just NH, a few H's. Attached to our first C are 3 H's. So I write CH3. Then attached to that again is another C, C to C. Attached to this C is only 2 hydrogens. So CH2. Attached to that is another C with 2 hydrogens, another C with 2 hydrogens, until we finally get to the last one, the last C, which has 3 hydrogens. So the semi-condensed structural formula for this specific alkane is CH3, CH2, 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 CH3. Okay, so these are the different types of formulas that we need to understand. Let us talk about naming. This is very important. We're going to talk about naming a compound. So we have prefixes depending on how many carbons we have. Very simple. If we have one carbon, our prefix is meth. If we have two carbons, our prefix is eth, then prop, bute, pent, hex, hept, and oct. Okay, so just depending on how many carbons we have. Can we say, yes, you could say that. However, you'd need to say CH2, 3. So someone's asking if we could condense it even more. CH3. Then you'd say CH2 and say that there's 3 CH2s and then end in a CH3. You could group them because here we have 3 CH2s. Okay. So our first step in naming is to identify the longest carbon chain. So you want in a row, okay, carbons, the highest amount of carbons, okay, in a row, okay, with no like disruption type thing. So in this specific case, all right, please keep in mind, you're not always choosing the straight line. Let's just I just want to make it a bit more clear that it's not part of like the main branch. Okay, so what are they saying? Yes, you're not always choosing the straight line. So the longest carbon chain is not always in a straight line. Let us consider, right? So we could start from the left, we start from the right. I'm just starting from the right. Okay, I'll get back to your question in a bit. Okay, so longest carbon chain, okay, if I start here and go on, okay, it's no different to me starting at the bottom. I could start with this carbon and move on, okay, or I could start with this carbon. So this one doesn't matter. I can start here. So when I'm going, I can either go to the end or I can actually go up, because if I go up, then I'm going to have this carbon and this additional carbon. So now I've created the longest chain. So instead of going straight, if I had gone straight, in my carbon chain, I would have had 1, 2, 3, 4, 5, 6, 7, 8 in total. However, if I went up, or if I go up and consider that one as well, I would have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I need to identify the longest carbon chain. Yes, you won't be responsible for 9. This is just an example to test out the longest carbon chain. But that's how I would identify it. Then everything else, like this guy and this one, they'd be what we call branches. Okay. And the longest carbon chain is what we refer to as the main branch. Okay, the longest, once we've identified the longest carbon chain, we refer to that as the main branch. Okay, now we talk about numbering. Okay, how do we number? Okay, because we have to actually number them. So where do we start numbering from? Because this carbon chain, okay, it's that whole thing. But do we start numbering this 1, 2, 3? Or are we supposed to start from the other side? So that's what we mean when we say numbering, okay? Because we need to number our carbons so that we can label them, okay? So when it comes to numbering, okay, so let's work with our worked example here. Let's look at this example, okay? We have to identify the longest carbon chain. Somebody tell me how many carbons are in the longest carbon chain in this question. How many carbons are in the longest carbon chain in this question? Okay, you say 9. I would have to disagree with 9. 8. Okay, correct. 8, right? So generally you start on your straight line, okay, and see if your straight line leads you to anything. But like, let's look at this, for example, C2H5. Okay, now C2H5, this is like in semi-condensed, or like it's not in structural formula. So C2H5 could be written as C, 2 C's and 5 H's. C2H5. So if I start here, it's no different to me starting there, because by the time I get to this C, I have 3. And if I start here, by the time I get there, I have 3 as well. So it's no different. Okay, so I can start here or here. Doesn't matter. I'm starting on the straight line, just so it's easier to visualize. Okay, C2H5. So I start here. Okay, now I reach this C where I can see a C up and a C down. I don't go there because I know I can get more C's if I go this way. Then eventually I get here, I can either go down or left. It doesn't really matter. I'm just going to go left, so it's easier to visualize. Okay, so now I've identified the main branch, okay, the longest carbon chain, and it has 8 carbons. Okay, that's fine. So step number 1 is done. Longest carbon chain is done. Now numbering. We have 3 criteria for numbering. The first one is you would start numbering on the side closest to a double or triple bond. Okay, so whichever is your longest carbon chain, you would start numbering. Your first criteria is if the side that's closest to a double or a triple bond. Okay, second thing, closer. So basically, when do we follow the second one? If the first one, meaning, so if the first one doesn't hold up, meaning that what if there's no double or triple bond? So if there's no double or triple bond, we move on to number 2. Alternatively, if we have a double or triple bond, but they are equidistant, okay, let's do an example of that. Let's just say, oh no, why did I just close? I'm not going to draw in the hydrogens. Okay, let's have a look at the simple compound. Tell me, what's the longest carbon chain in this compound? How many carbons are in the longest chain? 4, exactly, right? There's no more, no less. We have 4, okay? So this is our carbon chain. Okay, let's talk about numbering. Now we have to number this, and the first criteria says closer to a double or triple bond. So which side is closer to a double or triple bond? Left side or right side? None of them. Because how we judge is we say, okay, let's look here. If we start numbering on the left, 1, 2, 3, then on the first carbon, we have a double bond. If we start numbering on the right, 1, 2, 3, then on the first carbon, we have a double or triple bond. So in this case, this is what we refer to as equidistant. So when they are equidistant, then we move on to number 2. Okay. They say any closer group. Okay, so this is the second criteria. From the left or from the right, or whichever side we're starting, whichever side is closer to the group, we start numbering from that side. When we talk about groups, we talk about the following. We have a methyl group, which is basically 1 carbon. Okay, and obviously it has its 3 respective hydrogens that it's bonded to. But when we say methyl, okay, if you remember me saying from earlier, meth or meth refers to the prefix for 1 carbon. So when we have a methyl group, it's CH3. Then we could have an ethyl group. That's when we have 2 C's, H5. So C2H5. These are known as our alkyl groups together. Alternatively, our groups could refer to a halogen, okay, or a hydroxyl, which is basically OH, which makes it an alcohol. Okay, methyl, ethyl, halogen, hydroxyl. Right. So that's when we talk about groups. So if there's a methyl perhaps, or an ethyl that's closer to any side, that's when we move on to B. We say, okay, we start numbering from that side, which is closer to any group. What happens if the groups are also equidistant? Then you would label it in alphabetical order. Okay, following this. So obviously we have halogens. Okay. So your halogens are bromine, chlorine, iodine, and fluorine. The words that we use for them are bromo, chloro, fluoro, and iodo. And then we also have our ethyl methyl. So it doesn't matter. We don't distinguish between any of the groups. All the groups, we just label it in alphabetical order. So bromine will come first if there's a bromine present. Chlorine will come second if it's present. Ethyl third, fluorine, iodine, and then finally a methyl. So literally in alphabetical order. Okay, so let's look at our example and let us try and number our example. Okay, so number one, we're going to look for a closer double or triple bond. We're going to look for a closer double or triple bond. If the double or triple bonds are equidistant, we move on to B. Okay, we move on to B, which is any closer group, and then eventually alphabetical order. Okay, so we'll do examples. So now tell me, is there a side left or right? Because we just chose the straight chain because it's the longest. Is there a side left or right, okay, that is closer to a double or triple bond? Left, correct, 100%. Okay, the left side is closer to the double bond. How do we know? We count. So here's my first carbon, then second carbon. So already on the second carbon, we have a double bond. So on the second carbon, double bond. But if I had to start this side, 1, 2, 3. On my third carbon is a double bond. So therefore, that's not the closer side. The left side, actually, there's a double bond closer. If I had to move this double bond over, all right, if I had to move that double bond over, now, in this case, we would not be able to say that there's a side that has a closer double or triple bond. Why? Because when I start on the left, I can see that 1, 2. On my second carbon, I have a double bond. When I start on the right, 1, 2. I see on my second carbon, I have a double or triple bond. Okay, so now I have to move on to criteria B, which is any closer group. Okay, so remember, just to revise, we said that we have methyl as a group, ethyl as a group, halogen, hydroxyl. Okay, so let's talk about it. Let's look at this examples. So actually, I can see many different branches or groups. Firstly, here, this is CH3, just in structural formula. This is CH3 and CH3 again. Those are in. Yeah, I saw your question. I said I'll get to it in a bit. Let's finish this naming and I'll talk about it at the end. Okay. This is in semi-condensed structural formula. Okay, so too is C2H5 in semi-condensed structural formula. So I am seeing all my groups. Okay, actually I have a ethyl, ethyl, ethyl. So anything that's not part of the main branch, by the way, is a group. So only these C's, because we've identified the main carbon chain, we've identified the longest carbon chain. Okay, once you identify the longest carbon chain, all the carbons in that carbon chain form part of the main chain. Okay, what do we call it? Main chain. Okay, and anything that's not part of the main chain, any carbon that's not part of the main chain, that is what we would refer to as a group. Okay, obviously we have to definitely choose the longest carbon for it to be correct. We have to choose the longest carbon chain for it to be correct. Okay, so yes, the blue highlights, those are my groups. So now tell me, which side has a closer group? Left, correct. So in that case, I'd start numbering. In this one, I'd start numbering for that. So 1, 2, 5, 6, 7, and 8. Okay, let's change it up a bit again. I saw something about so I see that fluoro, but my teacher says that's wrong. She said it's fluoro. Okay, I think it's a spelling thing. I'll double check the spelling for you as well at the end. Okay, so let us get rid of these guys. Okay, so again, criteria number 1, we can't follow it in this case because there is no double or triple bond. Okay, let's have a look at this. Criteria number 1, closer to any double or triple bond? In this case, we don't have a double or triple bond, so we have to move on to number 2. B, any closer group. Now, if we look carefully, if I start from the left, 1, no group, 2. I already have a group on the second carbon. Now with the changes I made, 1, 2, I also have a group on the second carbon on the right-hand side. So that's when we fall to criteria C. Alphabetical order. You do this when they are equidistant. So my groups are equidistant. They are both on the second carbon. Okay, so alphabetical order. Bromo, chloro, ethyl, fluoro, iodo, methyl. So in this case, I have a methyl. And I have an halogen, which is fluoro. It's just a U. Okay, we'll double check to confirm with ourselves how to spell. So in this case, where would I number from? Left or from right? Someone says right. Do we agree with them? Okay, correct. We start labeling from the right because F comes before M. Okay, fluoro alphabetically comes before methyl. Okay, let's go back to what it was originally. Okay, perfect. So now let's just revisit it. Actually, we said that this one, okay, we're going to start labeling it from the left. So 1, 2, 3, 4, 5, 6, 7, 8. And the reason for that was because the double bond is closer to the left side. Okay, so the original compound that we had fulfills the first criteria of you need to start numbering closer to the double or triple bond. Okay, so now we name. Since we are done numbering, now we can name. So name, okay, always follows this order. We will put our halogens first, then our ethyls, then our methyls, then the parent. Okay, the parent is basically which homologous series it belongs to. And we also, in our parent, need to indicate the position of the functional group. Okay, we'll get there and we'll do that. So halogens, ethyl, methyl, parent. That's always the order. As you can see here on top, what does this mean? This basically means that when we have two numbers next to each other, we will use commas to separate them. If we want to separate a number and a word, we will use a dash to separate them. Now tell me, to which homologous series does this compound belong? This compound we're dealing with. To which homologous series does it belong? Alkene, 100%. And we know that because we can see the presence of the double bond. As soon as we see double bond, we know that it's an alkene. Okay, so then we name it halogens, ethyl, methyl, parent. So when naming, we need to indicate the position of everything we're naming. So does it have any halogens? No, so it's fine. We just move on. Does it have an ethyl? Yes, it does have an ethyl. So how I name it is I mention the position of the ethyl. If I look at my ethyl, which is C2H5, okay, I can identify that it's on the 6th carbon. Okay, so provided that our longest carbon chain is correct and we have labeled or numbered correctly, then of course this is going to be correct as well. So I will label this 6 between numbers and words. I have a dash. So 6-ethyl. And I've allocated for the ethyl and I've allocated for the position of the ethyl. 6-ethyl. What about my methyls? How many methyls do I have? Someone tell me, how many methyls do I have? 3, correct. So since I have 3 methyls, I will need to account for all 3 methyls. Okay, so now I need to say, I need to account for the numbers. So I'm working between letter and numbers. So what color are the methyls? That's a very strange color. okay, the methyls were at position number 2 and position number 4. I have 2 of them. So I will account for all of them. I will say -2, 4, 4. I will mention it twice. This indicates to me, okay, I have 2 methyls at the position 4 on the 4th carbon. Okay, so 1, 2, 3. 2, and then between numbers you put in comma. So 2, 4, 4. Right, now I'm done. No, I'm not done. I need to say methyl. So I need to say dash methyl. But because I have 3 methyls, I will actually use a prefix and I will say trimethyl. I will use the prefix and I will say trimethyl. Okay, hope that makes sense. Let's write our prefixes here. So 2 is di and 3 is tri. You shouldn't go more than that. Okay, so done. I've accounted for my ethyls, I've accounted for my methyls. Now my parent. Okay, so the parent is actually, you're going to use the homologous series, and you have to indicate the position of the functional group. So what is the functional group of an alkene? Someone tell me, what is the functional group of an alkene? Describe to me the functional group of an alkene. It's a double bond, exactly. So my functional group is here and here. I actually have 2 functional groups. Okay, so I have to allocate for both. So again, okay, so now I'm going between English and English, like word and word. So I don't need to have a space. Okay, so I can just I can just directly write whatever I'm going to write for the parent immediately after methyl. Okay, now the parent, okay, is basically, it's an alkene, number 1, but it's not just any alkene. Okay, it is an alkene that has 8 carbons, so it's actually called octene. Okay, we didn't go through these properly, so we can go through them now. Meth, eth, prop, bute, pent, hex, hept, oct. These are prefixes. I'll write all the suffixes here as well after this. These are prefixes. We know prefixes from English. It's the words that we begin with. So whenever something has 1, okay, then we have the suffix. So for each homologous series, they have their own suffix. Ein, ol, oic acid, O8, L1. Okay, we'll get used to them. Don't worry if you're confused by them. So for example, if I have an alkane with 1, if I have an alkane, so we know alkane is ein. Okay, if I have an alkane with 1 carbon, I will call it methane. If I have an alkane with 2 carbons, I will call it ethane. If I have an alkane with, let's just say, 6 carbons, I will call it hexane. Okay, let's do an alcohol. An alcohol suffix is ol, all. Okay, so if I have an alcohol with 1, I will call it methanol. If I have an alcohol with 6, I will call it hexanol. If I have an alcohol with 4, I'll call it butanol. Okay, so that's how we utilize our prefixes and suffixes. So the suffix here is in, the prefix is oct. Okay, so basically it is octene. That's what we're dealing with. That's the compound we're dealing with. Okay, but we need not forget this critical information to indicate the position of the functional group. So we need to indicate the position of the double bond. Okay, so how we could do it, one of 2 ways. We could say oct, and then before we talk about before we talk about the fact that there's a double bond, okay, I will put the positions. So my double bonds are at carbon number 2. So you always choose the first carbon that it's attached to. So I'll choose 2, not 3, and 5, not 6. So 2, 5. So oct 2,5, between numbers you put commas, between number and letter you put dash. 2,5 oct in, but again, prefixes for the groups, okay, for groups, I guess, and the parent. Because we have two double bonds, we will say die. Remember, in indicates double bond, and die-in indicates two double bonds. So 6-ethyl 2,44 trimethyl oct 2,5 in, die-in. Okay, you could also mention your position of your functional groups first. So methyl 2,5 dioctene. Dioctene. Okay, I don't know. I've always used this one and I just prefer that one, but you can also utilize that one. This one just makes more sense. You break it down. Okay, so that's how we do naming. We'll do some more practices, and then we'll take it from there. Wouldn't the brackets represent a branch? Okay, so I'll get back to this question. This person asked, wouldn't the brackets represent the branch? Where were we? We're talking about semi-condensed. Okay, you see this also, right? With regards to semi-condensed, okay, you have to understand how it looks. So in this case, brackets do represent branches. However, in this case, it would not. I'm just trying to think, are you supposed to put a big 3? I'm going to confirm whether you're supposed to put the 3 for this before, or you're supposed to put it as a subscript. Okay, because you might need to put it as a 3 before so that it differs from a group. Okay, but what would indicate to you that it's not a group is the fact that this carbon, the first carbon, the carbon to the left of it, has 3 hydrogens attached. So it only has 1 bond. So it cannot have 3 more groups of CH2. This previous carbon cannot have 3 more groups because it doesn't have space. It only has space for 1 bond, and it bonds to this carbon. Okay, and it bonds to that carbon, and we put it as a subscript. Not subscribed, subscript. Okay, so yes, in that case, that's what would indicate to you. Okay, so you need to understand that part of it. Okay, I hope that makes sense. So whether it's a subscript or a coefficient, you need to see that the previous carbon has 3 hydrogens, so it's impossible for this to be a group. It's indicating multiple CH2s. Okay, so next time we come back, we'll complete esterification, isomers, and move on to intermolecular forces and organic chemistry. And eventually we'll get obviously to reactions, and we will do some questions and everything. Okay, cool. So all the best for those of you who are writing. Sorry, I didn't see the YouTube chat. I forgot to open it, but can you have a double bond? No. Someone's asking, can you have a double bonded to your alcohol? No. The answer to that question is no. Okay, YouTube question. Okay, perfect. Shukran. Amin. Okay, all the best again for you guys' test. Have a good week of school. If you're not writing, then you're lucky, but I'll see you guys next week, same time. Okay, where we'll finish up organic chemistry. Thank you guys.